let's get this started. So we're going to do a couple things today. The first thing I want to do is I would like to start, and I would like to talk about your quiz on Friday. On Friday, you will have an 8-question quiz. Okay, 6 of them are going to be over phase changes and graphs and things like that. And then 2 of them are going to be over Q to Q calculations. One has a lot of support and one has very little support. So we're going to practice both of those things today so you guys feel ready for that quiz Friday. Tomorrow we have a lab that we'll do in class tomorrow with you, cohort. And cohort B, you'll do this when you come back next week. So nobody has to call in next week or tomorrow. And then Friday is just the quiz. If you're taking it at home, it's open between 7:30 and 1:30 per usual. Okay, so the first thing I want to do in your packet is I would like for you to find the What's That Metal lab. What's that metal? What is that metal? Perfect. And so what you see here is I have a piece of metal. It's on a string. You can see, got some metal. And the main objective here today is to identify the unknown metal by calculating the specific heat capacity. So there are 4 options as to what this metal might be. Okay. And these are the same calculations we were doing last week. So if you felt comfortable with that, you're going to knock these out. It's going to be an easy day. If you don't know these calculations, it's going to be okay. This is your day to practice. So we got to do a couple things. There's a list of items you're going to do. First thing, I'm going to get the mass of some cups. Let me re-zero that. Empty cups go on here. 9.83 grams. And then I'm going to get the mass of the metal. Metal going right onto the scale here. Let's do it. 55.14 grams. Oh heavens, that's the wrong spot. Read your labels. Mass of the metal. And then we're going to do the rest of this kind of once we get this metal going. The next thing I have to do is I have to take my metal to a temperature that I know that it can start at. So I'm going to put my metal into this hot water that is just now starting to boil. And we're going to boil it for 5 minutes. During those 5 minutes, it's 17 after. Okay. During those 5 minutes, I'd like for you guys to do a little bit of practice. So actually, you have to move backwards in your notes. I'm sorry. Go back one. And it says, oh, maybe it's forward. Just kidding. Oh. Forwards. Phase change review and Q to Q practice. So what I want you to do is answer these 2 questions. It's just a review of what we talked about on Monday, but I know it's been forever since then. And then I would like for you to be able to fill in this graph for water. Okay, tell me what's endothermic, exothermic, where are the temperature, most important temperatures for water, where are the phase changes, where are the actual phases. So you're going to do all that, and then we will do the back here at the end of the period, so don't worry about that. But we are going to, perfect, get some of this stuff going. So you got about 5 minutes while this is boiling. I'm going to take attendance of people at home. The phase change review and Q to Q practice. You guys are knocking this out. Let's do it. Beautiful. All right. Let's see if you can answer those questions. Little review for what you're going to see on your quiz. We are boiling away here. I'm going to take some attendance. All right, are we ready? We did everything. Feeling good? We're ready to get started. Let's do this then. All right, when you place a beaker full of water over a Limp-Bug subverter, why does the temperature increase? So the molecules are moving faster. The reason why is because, not when this is boiling, obviously temperature's not increasing right now, but we are giving energy to the water, and then the water is moving faster. Temperature is a measure of kinetic energy in a substance. So the particles move faster, everything goes faster. Correct? But then when you, right now, if I were to take the temperature like we did on Monday, the temperature stops and stays right around 100 the entire time it's boiling now, because now it's changing state. When you change state, we're still giving it energy, but the energy you're putting into that water is allowing that water to go from a liquid to a gas, which requires a whole lot more energy. Okay? Perfect. So we're not raising the temperature. We're now just going through a phase change. Let's talk about these phase changes on the water graph. The two numbers that are very, very important is 0 degrees Celsius and 100 degrees Celsius. If you have flat lines at anything other than 0 and 100, you are not water, okay? But you will have this type of graph for every substance. Every substance has a boiling point. Every substance has a melting point. It's just some of them are really, really high or really, really low. Okay, but this is water. So when we are below 0, water is a solid, and it can warm and cool. That's why the line is at an angle. Okay, it can warm and cool. But once it hits 0, and this is extremely important for next week. That's why I'm hammering this real hard. It will stop changing temperature. It will start changing phase, and it will melt. It will stay at 0 the entire time it melts until it's now liquid at 0. Okay, liquid at 0. Then the liquid can go from 0 all the way up to liquid at 100. But once that liquid hits 100 degrees, it's going to stop and it's going to boil. And that's going to boil and boil and boil and boil until it is a gas at 100. And then it can continue to heat again if it would like. That is when you're putting energy into it, and that is the endothermic look. Okay. You can go back down. My gas can cool. It can condense at 100. My liquid can cool, and it can freeze at 0, and then my solid can cool down again. In order to do those things, to cool and to condense and freeze, you need to remove energy, and that is exothermic. You take energy out of it, and it's an exothermic process. Okay? So we're feeling good with that. Phase changes are not the hardest. It's going to be more just graph reading at the end of the day, and knowing what happens to the temperature and particles and things like that. Okay? So 6 of the questions on Friday are about that business. Awesome. Our boat has been boiling for a pretty good time now. Let's go. Now you have to go backwards. Let's go back to the lab. And let's get some data, because also on your quiz are these Q to Q calculations, if you will. Q to Q calculations. So I'm going to put my cups back on there. Make sure they're still, yep, 9.83. This time, because the metal is a little bit larger, usually they're around 30 some grams. It's around 55. I'm going to use a little bit more water. So I'm going to get 100 mils of tap water here today. Doesn't have to be perfect because we're going to take the mass of it anyways. But, you know, if it says 100, I like it to be 100. Wonderful. I'm going to take this water. I'm going to pour it into the cup. Now, I'm not going to write this number right here where it says mass of 100 mils of tap water. Off to the side, we're at 108.23. 108.23 grams. Because that is the mass of the cups with the water in them. What do I have to do with those two numbers in order to figure out what the mass of the water is that I just poured in there? Let's subtract it. Real-time data, let's do it. 108.23 minus 9.83. What did everybody get? 98.4 grams is what I got. Check me, make sure I'm right. Feeling good? Awesome. Now, it says we also want the initial temperature of the water. So I'm going to move that, fan ram, turn that on right here. We're going to give it a second. Now I want to think about what's going to happen to the temperature. We're going to have some cool water in here. This bolt we boil things a lot in this class because by boiling it, I know that this bolt is at what temperature right now? It's at 100 degrees. It's been in that water for like 10 minutes, okay? So that's at 100 degrees. My water, oh, it's a pretty number today, is 23.0 degrees. When I take my 100-degree bolt and I throw it in my 23-degree water, what's going to happen to the temperature of the water? It's going to go up, and my bolt is going to cool down. And they're going to meet, and we're going to write that temperature right there, correct? All right, so move this out of the way. 1, 2, 3, super fast. Exchange. Don't want to lose too much energy to the air. We're pretending all the Q goes from the bolt and only into the water for this lab. All right, we're going up. We're going up 26.6. Can we go up any higher? 26.7. All right. Looks like it's settling there at 26.7 degrees. 26.7 degrees Celsius. Okay, so now one of these on your quiz is going to be very open-ended. It's going to say, just tell me which metal this is, okay? So almost exactly like this. And one of them is going to have a little more to kind of give you some points and give you kind of a refresher on how to do it. The main idea here that I know is that Q is equal to MC delta T. And I know Q of whatever the water gained is equal to the Q of whatever the metal lost. So if you can calculate one of these Qs, you're well on your way to answering this question. I know I don't know enough about the metal. I'm obviously trying to find the C value, the specific heat capacity of the metal. But what I can figure out is the Q of the water. So let's write QH2O is, and if you remember what you're doing from last week, I'm going to kind of give you a few minutes to try to go through. If you don't remember, that means if I want Q of the water, that means here I want M of the water, which all you have to do is look in the data table. I want C for water, which you should have in your brain. It's your new favorite number. And I want the delta T for water. And you're going to multiply all three of those things together. Okay? So if you know where you're going, you can go further than that and finish the whole question if you would like. But at the very basic, you have to figure out the Q of the H2O. Okay, you should have M, you should know C. Delta T is a quick calculation to get it. Let's see who can get this first part filled in for me. And try this at home. Hopefully you're feeling good as well. Plug in these numbers, MH2O, CH2O, and delta T H2O. Let's do it. I'm going to start to do this calculation myself. And if you guys have any questions at home, please don't hesitate to yell on out to me. I need these numbers. I'm going to come around and see how you guys are doing here. So hopefully you got some work on your paper. I'm going to come around in a minute. Let's see who can. Your quiz will look just like this on Friday. You have 2 of these questions. Let's see if it got good data. Oh, yeah. Nice. All right, we got some good numbers. I'm going to come around and see where everybody is at. Anybody at home have any questions on how to find these three things? Anybody? Questions on how to find? All right, so let's check back in here. We got some people done. We got some people halfway. We got people all over the place. That's okay because we got 2 more practices after this. We're going to do great. Now, the mass of the H2O. That one, my friend, get out of town. That's on the wrong side now. The mass of the H2O, you already calculated up here. And to be honest, on the quiz on Friday, I'm not going to give you the cup stuff. I'll just give you this information. So you always look and you see this is the mass of water. So I'm going to put 98.4 for my mass of water. 98.4. C value for water never changes. C value for water is, thank you, 4.18 joules per gram degree Celsius. Delta T for water, that one can be tricky. Let's see. Well, if the water was at 23 degrees Celsius and it went up to 26.7 degrees Celsius, how do I know how much it changed? You subtract. So 23 to 26.7 is 3.7 degrees. Do we agree with that? Awesome. When I multiply those together, I'm going to get the Q value of my water. So we multiply in your calculator. I know you got it. Come back over here. I got 98.4 times 4.18 times 3.7. When you get that, the Q of the H2O is 1521.85 joules. Everybody feeling good on that? You have to know the unit. Q is joules. Now, because of the law of conservation of energy, that's how much energy was gained by the water. That's exactly the same amount of energy that was lost by the metal. So if I know the Q of the water is also the Q of the metal, do you also know the M of the metal? We are looking for the C of the metal, and then the hardest one, be very careful, the delta T of the metal. Think about how you would figure out the delta T of the metal, okay? The water went from 23 to 26.7. The metal, why did we boil it? What temperature did we try to get it to by boiling it? We got it to 100, and it went from 100, and they met at 26.7. So think about how you get that delta T. So then you're going to say, this is my Q. So Q of the metal is actually 1521.85 is equal to the M metal, which you should be able to find up in your data table, times, I'm looking for C of the metal. That's what I'm trying to do. Delta T metal. Okay, so you just have to find and plug in 2 things and then solve for C. Walk it around again, unless anybody at home lost so far, please talk to me if you are. Please, please, please. Okay, that's a no. Let's see who can get this right. The M of the metal, super easy to find out. That was just 55.13, 55.13 grams. C is what we're looking for. And then the hardest part sometimes is people figure out the delta T of the metal, okay? My water went from 23 and it warmed up to 26.7, but my metal was at 100 and it came down to 26.7. So that delta T, I need to subtract 100 from 26.7 and you get 73.3, if I'm not mistaken on that. Okay, then how do you, this is just algebra at this point. How do we solve for this? Well, I'm going to bring down this number, 1521.85 is equal to, I'm going to multiply 55.13 times 73.3, and I get 404103, and then I have my C there. In order to get C by itself, what I need to do, because if I told you 4 is equal to 2x, you would be like, well, that's easy. I just get rid. There you go. So you would divide 4 by 2. Exact same thing here. You just have 1,500 is equal to 4,000x. So I'm going to take this, and I'm going to divide both sides by the number that's stuck to my variable, 4041.03. So that gets rid of that number, leaves C by itself. C is equal to, when I do 1521.85 divided by 4041.03, the number that spits out of my calculator when I round it was 0.38 joules per grand degree Celsius. Yes, you have to know the units. And then if you take a look up at the metal, my friend, the options, okay, the only one that's close to 0.38, that metal is, and absolutely is, if you couldn't tell by the color, made of copper, okay? This is just a piece of copper tubing. So you got that. Does that make sense? So now I did one for you. Now it's your turn to do a few by yourself. What I have on the back of the worksheet that you guys had here, phase change review and Q to Q, you have 2 more practices, okay, that I'm going to offer very little help on because I want you to be able to do them. Now, the first one is calculating the C value, the specific heat capacity of a metal. That looks exactly like one of them that you will see on the quiz. The other one on the quiz, you're going to have to identify the metal, like the lab. And then for those people that are like, well, I got this. This is easy. I added one with a little bit of a twist to it. You won't see this on the quiz. But again, if you can do the harder ones, the easier ones will come with no worries to you. If you would like to see the key is in the Wednesday folder. So why don't we go ahead and do this? Go ahead, fire up your Chromebooks. Go into week 11, because you're also going to do your participation points. In the Wednesday folder, go ahead and do your participation points. You can just say that you came to class yesterday, because I know you will. And then the key to this business is right here, so you can check yourself as well, okay? I'm going to give you guys the last, you got like 9 minutes. I highly suggest doing these, okay, because this can be extra tough math-wise, okay? That was super good. I'm going to check in with everybody at home, call them out, see how they're doing. Then I'm going to come around and make sure everybody got some work done here. So determination of the specific heat capacity of a metal. I'd like to know that specific heat capacity. Let's do it.